The story starts in the early 1950s, when the Met Office, a small government department based in Dunstable, was the only organisation charged with protecting the British public from weather. Its staff used techniques refined during the Second World War, gathering data from around 500 UK weather stations. They drew charts of low-pressure systems and weather fronts, and then used their judgment to make a forecast.
In the 1950s, meteorologists were still using methods that were really sort of decades old. So science was being used. They were capturing their ideas in terms of synoptic charts, and these were very useful for forecasting the weather, say, 24 hours ahead. But it was still very much a hit-and-miss affair.
Things may have stayed like this for years, but then, in the most sudden and savage way possible, the weather itself intervened.
I'm in the North Sea off the coast of Essex. It's calm here today, but on the night of January the 31st, 1953, a huge storm surge tore through this area, causing one of the worst natural disasters in recent British history.
It was a perfect storm. A low developed over the Atlantic, which swept around the top of Scotland. The air pressure dropped so much, the sea level rose by ½ a metre. This coincided with an unusually high spring tide. Then vicious northerly winds tore down the east coast at 60 knots, nearly 70 miles an hour.
That combination was deadly. In some places, the waves were up to 20 feet high. They battered this coastline and overwhelmed sea defences. The result was utter devastation.
Canvey Island in Essex was inundated. Local councillor Ray Howard was 11 at the time.
We all went to bed early, being it was such a foul night, but not realising that soon after going to bed, woken by my sister, who come rushing into the room saying that there was water gushing down the street.
From Kent up to Lincolnshire, families like Ray's were stranded.
The water was getting deeper and deeper, and then we saw boats coming down the street with army personnel in, and obviously they were shouting to say that they were going to start evacuating.
Across England, Scotland and the Netherlands, 32,000 people had to be evacuated, and more than 2,000 died. Communities would take years to recover.
We came back onto the island and it was a different place. I mean, the devastation those floods caused was unbelievable. The thing that will always stick in my mind is when I return back to my school and to see that boys and girls that you was in your class were not going to return.
So how did the forecasters get it so wrong?
There would have been some indication. The observations we collect would have allowed forecasters to see the fact there was a depression, that it was moving, and roughly what its track would be, and some sense that that could result in floods. However, there wasn't a warning system. This is the big difference now. There wasn't a way of communicating that risk to the public, or to the police, or the fire folk, in a way that they could do something about it.
Action was urgently needed. The government immediately began to rebuild Britain's flood defences. And for weather forecasters, the storm was a transformative moment.
The storm of 1953 shocked the Met Office into action. The first thing they did was institute a nationwide warning service for storm tides. But they knew they had to go further.
The first priority was to improve how to inform the public about the weather. Fortunately, the early 1950s saw the widespread adoption of television. By 1953, more than 3 million Britons owned TVs. To exploit this, the Met Office and the BBC set about making forecasts more watchable by introducing on-screen presenters.
Well, as most of you will have realised, it's been a very much better day today. In the south of England, it has been for quite some time.
This is their first attempt at this new approach. A trial filmed in the autumn of 1953 with the Met Office's Jack Armstrong.
However, it's not going to last very long. As usual, there's another depression out in the Atlantic.
BBC Television began regular broadcasts like this in early 1954.
By tomorrow, it is expected to be through into the extreme northeast corner of Scotland by midday.
But the problem went beyond communication. Forecasters in the 1950s could reliably predict weather up to 24 hours ahead. But the 1953 storm showed that this wasn't enough time when warning large areas of the country. Forecasters had to find a new way of doing things.
What they couldn't do was to really exploit the mathematical and physical underpinnings of the subject. So this is it. If you're going to break that barrier, go into 2 days, 3 days, then you've got to be able to use the underpinning mathematics, you know, in a more powerful way.
It had been known since the 19th century that the weather's behavior obeys just 7 mathematical equations. For a long time, scientists had theorized that they could be used to improve forecasts.
These 7 equations tell us how wind speed and direction, pressure, air temperature, humidity and density all interact with one another. So it's something you can write down on one side of A4, and that is the basis of your model. It's as simple as that. The difficulty is in then solving it.
In 1916, an English mathematician, Lewis Fry Richardson, had tried to solve the equations of the weather. He'd attempted this in his spare time, between shifts as an ambulance driver in World War I. In doing so, he showed in principle that mathematics could be used to predict the weather.
It was called numerical weather prediction, a technique that might finally take the guesswork out of weather forecasting.
But the problem was the actual equations are mind-bogglingly complicated. Richardson laboured for 2 years just to make a 6-hour forecast. So the technique was theoretically sound, but far from practical. Then, some 30 years later, in the 1940s, a new invention changed everything. These are some of the first electronic computers. They soon found many applications, everything from ballistics to accounting, even airline reservations. But the question was, would they be powerful enough to produce useful weather forecasts?
Very soon, meteorologists had hit a massive problem. The weather is a complex and ever-changing interaction between air temperature, pressure, humidity and cloud cover. The computers of the 1940s just couldn't handle that much data.
Somebody had to make the equations of weather simple enough to run on these early computers. The person who did this was an extraordinary character. An American mathematician called Jules Charney, and his inspiration was music.
Charney once wrote to a friend to say that nature was a musician more like Beethoven than Chopin. What he meant was fewer, higher-pitched fiddly notes and more chords, bass lines and grand expressions. Imagine the weather is like a musical instrument. The high notes represent the ripples and disturbances that barely register, whereas the low notes, these are the things that really drive the weather system forward. What Charney did was to come up with a mathematical framework that allowed meteorologists to ignore and iron out these little ripples and disturbances and focus instead on the things that really mattered.
It was a crucial step. Charney had given computers a way to predict the movement of larger weather systems without getting bogged down in details like small local showers. Or at least that was the theory. Charney now had to make it work for real.
On Sunday the 5th of March 1950, Charney kicked off the world's first numerical forecast. He used a machine not too different to this one. This is the Colossus at Bletchley Park, and it was designed and built to crack German codes in the Second World War. The machine Charney had was even bigger, the size of a room, and it took an entire team of people working night and day to keep it running.
To test Charney's ideas, the team programmed their computer to recreate the weather across North America on 4 separate days in early 1949. They then compared the machine's predictions with the actual weather on those days. So how did it do? Well, the computer did correctly predict a low over America, but it got some major details wrong. The real low moved much faster and covered a different area to the simulation.
As it happened, their first forecast, and I quote, was uniformly inaccurate. But by looking at that, they began to understand how to do computer modelling, what the sensitivities were, how to develop them. And it set the starting point, I think, for what has now become the way that weather is forecast right around the world.
Charney's experiment ensured that modelling the weather mathematically was the way forward. Looking back, you have to admire these early pioneers for their scientific ambition.
I find it remarkable that those people who began to program these equations into computers and have the bravery almost to try and model something as messy as the weather in computers, using equations, the fact that they tried, I think, is incredible.
The pioneers of computerized weather forecasting would need all the bravery and determination they could muster. In Britain, the story of how computers became central to our meteorological science was as much down to individual personalities as it was to raw technical innovation. To tell it, I've come to one of the world's most advanced weather measurement facilities, and it's in Hampshire.
This is the Chilbolton Observatory. It's the biggest steerable radar antenna in the world being used for weather forecasting. It's gathering information about clouds. It's helping to steer meteorological flights, and it's even tracking weather satellites. If there's a symbol for how technological weather forecasting has become, this is it. It seems obvious now that something as complex as the weather would need equipment on this scale in order to keep track of it. But it wasn't always the case. When this kind of technology was being developed in the 1950s and 60s, many meteorologists were unconvinced that it would ever be useful to them.
In those decades, a real tension developed between man and machine. Many were unconvinced that the raw calculating skills of computers would ever replace good old-fashioned human judgment.
There was actually a great deal of scepticism in the community that even with modern electronic computers, they could actually do the calculations in a reliable way. In other words, they could see that there were plenty of pitfalls, plenty of opportunities for calculations to go wrong, and therefore they didn't really have the confidence that numerical techniques would actually be superior to a human forecaster.
Overcoming this attitude would need a strong character, someone who was both ambitious and a top-flight scientist. This is John Mason, a physicist with a long fascination for weather. He was appointed Director General of the Met Office in 1965, aged just 42. Dr. Stan Cornford was there when Mason first took over.
He didn't seem an attractive person at that stage, but in fact he was a very able man and he didn't underestimate his abilities.
Mason knew the world was changing, the economy booming. Growing industries like aviation demanded ever more accurate and detailed forecasts. And he was convinced that computers were the best way to provide them.
He ensured that we could use the best available scientific tools, I suppose, and in particular always making sure that we had the biggest and best computer that was possible, and Mason was a very firm part of that, and his leadership helped make it possible.
Mason was a man in a hurry. With older and wiser colleagues telling him that computers weren't really up to the task of weather forecasting, he decided to force the issue. In November 1965, he organised the Met Office's first ever press conference. There, he made an announcement from which there could be no turning back.
At the press conference, John Mason took the biggest gamble of his career. He said that from then on, all Met Office predictions would be based on computer calculations rather than just human skill and experience. Brimming with a confidence that many of his colleagues didn't share, Mason promised the assembled press something incredible: 2 computer-based weather forecasts every day that he said would be more accurate than anything they'd seen before.
Further raising the stakes, Mason handed out copies to each of the journalists present.
And here it is, the very first operational weather chart made by a computer. It might not look like much, but this is a landmark in modern weather forecasting.
The computer-generated chart predicted calm and settled weather for the next day for most of the country. It was vital for both Mason's reputation and the Met Office's future as a high-tech organisation that the actual weather matched this forecast.
Fortunately, the Met Office computer got it right. The forecast that it made for November the 3rd, 1965 was an excellent match for what actually happened in the real world. Journalists, even politicians, were impressed. That success allowed Mason to secure the funding he needed to remake the Met Office in his high-tech vision.
Mason's timing was impeccable. He'd put his faith in computers at a time when another spectacular breakthrough was about to take their ability to forecast the weather to new heights.
TIROS, meaning Television and Infrared Observation Satellite, is more than just a dream. This experimental weather satellite means that man's vision is no longer limited to looking up at the clouds gathering above him.
That was really the game-changing moment. That was when scientists realized the potential that if we could make measurements from space in a controlled way, i.e. with a satellite in a controlled orbit of the Earth, then that really would give us this all-encompassing global picture of what the atmosphere is doing now.
These are some of the first images of our planet from space, showing the global weather system. This one, taken of Hurricane Esther in 1961, was the first direct evidence for how such storms develop. Satellites greatly improved computer-based forecasting, which needs the best information about how the weather is behaving now in order to calculate what it'll do next.
Your computer models, you have to feed them with what we call the initial conditions. So the conditions of the atmosphere now, you need to know that perfectly over the whole globe. And frankly, when the satellites came, that was really a revolution, because that's what gave you these global pictures that we were waiting for.
From the mid-1960s, satellites and computers have given us a powerful way to calculate how weather systems evolve from their initial atmospheric conditions. It's perhaps the biggest reason why we can have such a close relationship with the weather today. From what we should wear to whether we should put the heating on. From what we choose to eat and drink to when we leave the house. Even how we choose to get around. Nowadays, it's amazing how accessible and how accurate the short-term weather forecast has become.
Northwest Fitzroy.
But despite this, the last 50 years have not been smooth sailing.
Occasional rain, moderate or good, occasionally poor. Lundy, Fastnet, Irish Sea, southwest 5.
We all take weather forecasts for granted, but they're by no means perfect. In fact, there are very recent examples of when they've gone drastically wrong.
Good afternoon to you. Earlier on today, apparently a woman rang the BBC and said she heard that there was a hurricane on the way. Well, if you're watching, don't worry, there isn't. But having said
this is probably the most infamous weather forecast ever broadcast in the UK.
On the 15th of October 1987, the BBC's Michael Fish joked with viewers about a hurricane that was rumoured to be heading towards Britain. He was dismissive of the idea.
most of the strong winds, incidentally, will be down over Spain and across into France as well. But there's a vicious-looking area of low pressure on our doorstep, nevertheless, around about the Brittany area, and that is going to head across the southeastern corner of the country, bringing, if nothing else, a lot of rain with it.
But what happened next? Well, we all know what happened next.
Good afternoon. The worst storms for hundreds of years hit the south of England early this morning, killing a dozen people and bringing the whole southeast to a halt. Gales of over 100 miles an hour smashed buildings and caused millions of pounds worth of damage. There was no warning. The weathermen were caught with their forecast down.
In the early hours of the 16th of October, the great storm of 1987 smashed into England as she slept. Winds of 122 miles per hour ripped across the southeast of the country. Roofs were torn from homes, power lines were down, road and rail networks were blocked, and in all, 18 people lost their lives.
Most of the damage was done by falling trees. Even huge mature ones like this were uprooted by the hurricane-force winds. Here on Hampstead Heath, many of them still lie exactly as they fell on that stormy morning.
Not surprisingly, people were furious.
Well, joining me now from the London Weather Centre is the BBC's weather forecaster, Ian McCaskill. Well, Ian, you chaps were a fat lot of good last night.
Well, we have been forecasting high winds and gales relentlessly since Sunday. I admit, we weren't forecasting hurricane-force winds, and that's what we got, and that's what we will get maybe once every 50 years, maybe once a lifetime.
By this time, meteorologists understood how a storm of this size develops. Fish and his colleagues had even forecast strong winds, as they recognised a massive low-pressure system moving in from the Atlantic. But the crucial moments when it suddenly intensified, just hours before making land, happened in a narrow band of the Atlantic between any observation ships or weather buoys.
It's impossible to know whether any lives could have been saved or damage avoided if the forecast had been any different. But what we do know is that the whole episode shook confidence in the Met Office. This is the organisation that was meant to protect us, to warn us against the worst effects of the weather.
Just as in 1953, this very public disaster was a wake-up call for forecasters.
Was that a bad moment for the Met Office? Well, actually on the day, probably yes. But in the longer term, no, it wasn't. It was a really good thing to have happened for us, because it made us think very seriously about how we can do this better. What science do we need to invest in? How do we transform our forecasting system so that this doesn't happen again?
As a first step, an internal Met Office inquiry called for an increase in the quality and quantity of weather observations off the southwest coast of England.
But that's not all. The Michael Fish broadcast was based on a computer model, and it forced the Met Office to look again at how they used computers to make their forecasts.
Computer models, based on the strict rules of maths and physics, were supposed to take the guesswork out of forecasting. How could they possibly have failed so dramatically? The answer lay in the fact that the fundamental mathematical equations of the weather contained a truth about nature that no one wanted to confront.
Our weather forecasting model is based on some mathematics that has a rather special property to it. And it's a property that makes weather very interesting and now and again makes weather forecasting very difficult. What they had to face up to after the '87 storm was that there was something else there that just couldn't be left out of the, if you like, the forecasting picture any longer.
In fact, the way scientists understood the world had to be completely revolutionized.
By the start of the 20th century, scientists saw the world like a clockwork toy. If you understood the parts of a system and how those parts interacted with each other, you could predict everything about that system's future, whether it's the orbit of the planets around the sun or a ball flying through the air. And weather prediction was going along similar lines. If you could understand how the air moved, then you could predict the weather. Unfortunately, a discovery in the mid-20th century shattered those dreams of absolute predictability. And it's something you've probably heard of: chaos theory. This told scientists that however perfectly they understood a system, making accurate predictions about its future were almost impossible. This completely changed how they saw the world. And for weather forecasters, it meant that uncertainty and unpredictability had to be brought right to the heart of what they were doing.
It all started with these unremarkable looking squiggles. But make no mistake, this is one of the most significant images in the history of science. The first ever proof of chaos theory. To tell the story, we have to go back in time, to 1965, to the USA and the Massachusetts Institute of Technology. Here, a mild-mannered meteorology professor called Edward Lorenz worked with early computers, generating weather models as a way to combine his two great loves, maths and weather.
Edward Lorenz had a setup a bit like this one. He'd input data here about the weather, things like temperature or air pressure. The computer would take those numbers, run them forward in time, then print out its results here as a graph. That, in essence, was the weather forecast.
Lorenz's model was incredibly basic, using just 3 mathematical equations to simulate how his initial conditions might change in a real weather system. But from his early results, it looked as though it was doing a good job, outputting weather patterns that seemed to mimic the real thing.
So far, so good. But Lorenz wanted to check the simulation, so he decided to run the whole thing again using the same starting data.
All he wanted to do was repeat the results from his first run, to prove that his model was accurate and reliable. But what he saw shocked him.
Lorenz expected that both his runs would produce identical graphs, and at the start that's exactly what they did. But very soon the curves began to diverge, and by the time you get over here, they're 2 separate curves altogether. And that made no sense. So why would the computer plot two different curves from the same starting data?
It was a mystery. The model itself hadn't changed, and as far as he knew, Lorenz had put in his data exactly as he'd recorded it from the first run. Why on earth was the second curve so different to the first?
The answer turned out to be remarkably simple. Lorenz's computer stored its data to 6 decimal places, but to save time, in the second run, Lorenz has only input the data to 3 decimal places. It was a small change, a fraction of a percent, but it made all the difference, and it accounted for those wildly different graphs that he saw.
This is the key idea in chaos theory. An immeasurably small difference at the start of a process can have huge consequences to how it ends up. And this effectively makes that process unpredictable.
One of the hardest ideas to get your head around in science is that while some systems are inherently predictable, others seem inherently unpredictable.
These unlikely visual aids represent the key to explaining what Lorenz saw in his results. And it's all to do with their shape.
This football is a sphere, and when I drop it on the ground, I know where it's going to end up. Even if I change the starting conditions and drop it from higher or at a different angle, I can predict its path. Things are very different for this rugby ball. When I drop this, I honestly don't know where it'll end up. Now, every time I drop this ball, it went in a completely different direction, which makes no sense because both of these balls operate under the same laws of physics. The only difference really is the shape. But that difference turns out to be crucial. Every time I drop this ball, even the very slight differences in the starting conditions, accidental ones really, will make huge differences in how the ball bounces around. And this is how the weather works. When Lorenz was making his computer models, he thought that weather operated a bit like this football, predictably. In fact, weather is much more unpredictable, like this rugby ball.
At its core, this is the very essence of chaos, where a tiny error at the outset doesn't make for a tiny difference in the outcome, it makes for a different outcome entirely. In the case of the 1987 storm, the tiny error came from missed observations of the atmospheric conditions in a small part of the North Atlantic.
So what this reveals is that actually just missing one bit of crucial information can now and again, and it should be stressed now and again, make a big difference. And that's the hallmark of chaotic behaviour in the atmosphere.
The lesson from the 1987 storm was clear. Computerized weather prediction had to be reformed so it could deal with the chaos inherent in weather. This is the European Centre for Medium-Range Weather Forecasts, near Reading. In the 1980s, Tim Palmer worked with a team here to come up with a new style of forecasting to combat chaos.
Hello, Tim.
Hi, Alec. How are you doing?
This looks incredible.
Yeah, well, welcome to the European Weather Centre.
So, just tell me what we're looking at here.
We're looking at an ensemble forecast. This is a modern way of doing weather forecasting.
An ensemble isn't just one forecast, but 50. Forecasters give their computer a range of starting conditions, rather than a single best guess, like they did before.
What we're seeing here are the 50 individual weather forecasts that make up an ensemble. They're run from almost but not quite identical starting conditions, and then we move these 50 models forward in time to next week, and then we look to see, do all these 50 forecasts stick together, in which case one can be quite confident about what the future weather is going to be, or do they all diverge and do their own thing? This is kind of shown more clearly actually here, where we've zoomed in on just a few of these individual members, if you like, forecasts. So, for example, this one would be a rather, I think, unpleasant day across much of the UK, blustery, cold, very windy type of day. Not the day to have a picnic by any means, but just move one member over, so 23 to 24, and this actually is meteorologically quite different. There's very little pressure gradient across the UK. It's sort of a reasonably nice day. There might be a shower or something, but it could well be a very pleasant day.
And so in each of these predictions, you're getting a spread of how the weather might change over the next 12 hours or 7 days.
That's right. We're getting basically 50 plausible, equally likely a priori estimates of the weather.
The clever thing about this ensemble method is that if the 50 forecasts are all similar, then we can be confident about what the weather will do. But if they're very different, we have to accept that we can't be sure what'll happen.
So this tool allows us to estimate that sort of degree of confidence or a degree of predictability ahead of time. So the forecasters these days on the TV will often talk actually about uncertainty. They know it's uncertain because they've looked at these 50 forecasts and they can see, you know, in half of them the low pressure tracks up towards Scotland, but in the other half it tracks across the southern England.
And built into this system is a way of preventing mistakes, as with the storm of 1987.
Suppose there are just 3 or 4 of the forecasts which have an incredibly violent and intense storm. You may not want to ignore that. And if those are situations where people's lives are at risk, for example, then that's a dangerous situation to be in. So pretty much all the way around the world now, this is the technique that's used because it provides not only the most likely such situation, but it provides probabilities of extreme weather and it provides estimates of confidence.
Ensemble forecasting really came into its own when the St. Jude's Day storm struck on October the 28th, 2013. It produced violent winds that were only slightly less powerful than the 1987 storm, and it took a similar path across the south of England. But the big difference was that in 2013, we were ready for it.
Warnings about today's storm were first given a week ago, giving people and the emergency services time to prepare. Unlike the great storm of 1987, which took weather forecasters by surprise.
A week's warning for the St. Jude's Day storm showed that satellites, computer models and ensemble forecasting have made a difference.
But let's go across and take a look at today's chart.
Compared to how they were in the 1950s, our forecasts have improved enormously. Our 5-day forecasts today are as good as the 1-day forecasts back then.
Well, that's the forecast. Bye-bye for now.
But what if we wanted to look further ahead? How good are we at predicting what the coming season will be like?
Hello again. Let's begin then with what should be good news for most of us. The Met Office have issued the long-range forecast for the summer. Here's a headline: we're more likely to need a barbecue than a brolly.
In April 2009, the Met Office prediction of a barbecue summer went badly wrong.
And there will be some rain at times, but we're not expecting a washout by any means.
As what actually happened was one of the wettest summers on record. And then, in the same year, the Met Office said the chances of a cold winter in the UK were only 20%. In reality, the entire island was frozen solid. Since these events, the Met Office has stopped issuing seasonal forecasts, replacing them with monthly outlooks.
The demand and interest for forecast at weeks and months, years ahead, is huge. The science of that arguably is very much in its infancy. We're beginning to understand the processes that affect weather those weeks and months ahead.
Long-term forecasts are hard because the effects of chaos increase with time. A 10-day forecast isn't simply twice as hard as a 5-day one. It can be orders of magnitude more difficult. To see why, I want to show you a simple experiment with a twist.
This is a simple pendulum. You'll have seen these in grandfather clocks or even demos in science lessons at school. And they're very straightforward. Even I could write you the mathematical equations that govern how this works and even tell you when it stops. But it doesn't take much to turn this very simple system into something completely unpredictable. This is a double pendulum. It doesn't look hugely different to what we had before, but watch what happens when I swing it. At first it's all very normal, but very soon it starts to behave completely erratically. Now physicists are terrified of the double pendulum because you can write the maths for this, but you can't solve anything. You can't predict what's going to happen, and you can see here this completely erratic motion. And it's because there's two parts to this system now. The top pendulum affects the motion of the bottom one, which in turn affects the motion of the top one. And this feedback causes all sorts of headaches if you want to know what's going to happen next.
Weather is full of these feedback loops. Factors like humidity, temperature, and air pressure all interact with each other as the trillions of atoms that make up our atmosphere collide on a global scale. So a small change in one variable can be multiplied across the others. This means the longer a system runs, the more unpredictable it can become.
This chaotic behaviour is the reason why, however good our observation technology is, however sophisticated our computer models, precise weather forecasts beyond a few weeks are still out of our grasp.
Chaos has always been there, but we no longer ignore it. Meteorologists don't speak about what will happen, but what might happen. And for businesses who have to calculate risks in the long term, knowing the probability of what the weather might do is crucial information. From the energy sector to supermarkets to civil aviation, forecasting is vital to the economy. And weather prediction itself is big business today, with more private companies than ever before providing thousands of forecasts every day. All this is possible because of our understanding of the chaotic nature of our atmosphere. But there's another frontier to atmospheric science beyond just predicting the weather. And it's become one of the most important subjects in modern science: predicting the climate.
In simple terms, climate is just the average of how the weather behaves over the very long term. So whereas in a weather prediction we might be looking a few days or weeks ahead, in a climate prediction you're looking decades, even centuries ahead. It's not easy to do, and there are a lot of uncertainties involved, but it's incredibly important, and we've been trying to do it for much longer than you might think.
Climate science hinges on understanding not just how our atmosphere moves around the planet, but what it's made of and how it interacts with the oceans and the land below. Any changes on this scale need decades to take effect. But we have been able to make predictions about their impacts. The first breakthrough was the realization that carbon dioxide, released by burning fossil fuels, might cause the planet to warm up.
In the 70s, I wrote one of the first papers on what the effects of doubling the carbon dioxide concentration in the atmosphere might be. Now, at that time, I thought of this as a bit of an academic exercise. But of course, now, here we are, it being one of the defining problems of the 21st century.
This effect has been on the world's agenda for some time now. But Julia wasn't the first person to discover it. She was picking up on work done much earlier. Our knowledge of man-made climate change dates back to an experiment done in the mid-19th century. I've asked chemist Professor Andrea Sella to recreate it for me.
Andrea, hello. How are
Hey,
you?
Alec, good to see you. Good to see
What is
you.
this remarkable setup you've got here? It looks incredible.
Well, this is a recreation of one of the great demonstrations that a man called John Tyndall did at the Royal Institution in the mid-19th century.
And so I can see lenses, there's a light source. What does this show me about anything?
Well, what Tyndall was trying to understand, really, was what was it in the atmosphere that absorbed different types of light? And so what we've got is a very, very intense light source, and it's giving out a combination of two things. One is that it's giving out loads of visible light, but the other thing is it's also producing what was then called radiant heat. In other words, you can feel the warmth coming from that lamp.
This light represents two things: the sun and the warmth that's radiated back into the atmosphere from the Earth's surface.
So what Tyndall showed was the fact that there was actually heat radiation, if you will, which could actually be focused down. And I'm going to show you that with a little piece of gun cotton. And what I'm going to do is I'm going to put it actually into the beam here. We're going to see.
What am I looking for?
Well, something might actually happen as the whole thing gets hot. Let's just see if I can get in the right spot.
It's incredibly bright right now.
Ooh.
Okay. That was obvious.
So clearly, this stuff has gotten hot enough to actually ignite. Now, yeah, it does smell a little bit. So what Tyndall did then was to actually systematically go through the various components of the atmosphere. And of course, those included, nitrogen and oxygen and water vapor and so on. And then he actually put carbon dioxide in between.
In here, you've got carbon dioxide.
I've taken a little bit of carbon dioxide in the form of dry ice. I've left it inside so that it evaporates. So that tank is completely full. And what I'm going to do is I'm actually going to put a little bit of the same cotton here, and I'm going to place it.
Are we expecting something
at
similar?
The focus? Well, let's see. Let's see what happens. So I've got it at the focus. You can see the way it's brightened up.
Still bright, yeah.
It's still bright.
Okay, this is less exciting, Andrea.
Well, exactly. The incredible thing is that you can leave this here for a very long time, and it just doesn't catch fire. The reason is because, in fact, this tank of CO2 is acting as a kind of filter along the way.
So this is absorbing the heat that would normally have passed straight through.
It's absorbing that energy. And so the result is that is going to get just a little bit warmer, but it prevents anything happening at the far end.
What's happening on this desktop demonstrates the warming effect of carbon dioxide in our atmosphere.
Function and all that's all good, but if you have more carbon dioxide in the atmosphere, the inevitable consequence is that the Earth's temperature will get higher and higher, slowly.
Exactly. And way back in 1855, John Tyndall suggested that if we continued to burn coal, which was, of course, the fuel of the Industrial Revolution, that the world would become warmer as a result.
He suggested essentially what we know of now as global warming.
The extraordinary thing is that we've known about this stuff for something like 170 years.
The implications of this experiment are still being wrestled with. In fact, understanding how our climate is changing and what the impacts might be is the biggest challenge faced by meteorologists today, shaping a new approach to the whole field.
So whereas I started my career having to understand meteorology and atmospheric motions and atmospheric physics, I now need to understand about ocean physics, ocean biogeochemistry, how plants grow, how sea ice, particularly in the Arctic, how that forms and melts. All those things we need to understand now if we're going to say useful things, robust things, about how our climate will evolve as we go into a warming world.
In the UK, many institutions share this huge task. Collaborating on projects like the Facility for Airborne Atmospheric Measurements, which operates dozens of flights a year to study our climate. Today, scientists on board will test an instrument that'll measure aspects of our planet in an entirely new way.
So it's really exciting to be on these flights. It's a new instrument and, We've been working on it for a very long time, so the chances to now see it flying and measuring real data is really exciting for me personally.
This brand new technology is the latest tool to carry on Tyndall's early experiments into how our atmosphere absorbs light and heat. It's designed to measure a key factor in how much radiation gets trapped in the different layers of our atmosphere.
Each of these channels is looking at a part of the spectrum where the atmosphere is different transparency. So some of them see quite well right through the atmosphere, and some of them only see the bit fairly close to where you are at the moment. And that's why we've got this spread in the amount that's coming down. So this one here isn't seeing very far away from us, so it's getting quite high amounts of thermal radiation, because what we're looking at is quite warm. Whereas this one here is basically seeing almost all the way through to space, and space is very cold. So this is giving us temperatures of about minus 250 Celsius. So not much radiation coming down there at all.
Of particular interest to Stuart is the effect of clouds. Some contain a high amount of ice, and these reflect the sun's rays back into space.
This instrument will measure a new thing. It's going to measure cloud ice. So once it's up on the satellite, it will be giving us daily global measurements of cloud ice content, which is a really important thing to get right in our climate models, because it's got a big impact on how much of the solar radiation gets down to the surface and how much of it gets reflected back up into space.
Once tested on the plane, Stuart's sensor will be launched into space on a satellite, adding to the vast network of weather observation systems that circle our planet.
When the very first satellite was launched, the models were pretty highly developed. We knew quite a lot about the atmosphere, but we didn't have many observations. We are now in the situation where one could argue we have more observations than we really know what to do with.
In the years immediately after the Second World War, Met Office forecasters received a few hundred observations per day. Now, thanks to everything from aircraft to a global network of satellites, they receive a staggering 106 million weather observations every single day.
Bringing those observations together, bringing those together in a coherent way, that's the challenge for science at the moment.
Making sense of all this data to figure out what it can tell us about our future is an enormous task. And it's one that the Met Office have to take on in order to uphold their commitment to protecting the British public from danger. That means building this, one of the two biggest weather computers in the world. It's the only one that can simulate both short-term weather and long-term climate simultaneously.
On every scale, this computer is enormous. It takes up 2 rooms, each one the size of a football pitch. It weighs the same as 11 double-decker buses, and it can compute 23,000 trillion calculations per second. But that's what you need if you want to simulate the entire Earth and all its weather systems.
The computer code running in this machine has taken 100 scientists 10 years to write. It's a virtual planet Earth, complete with simulated weather that churns about the atmosphere with astonishing accuracy. This single tool is both a magnifying glass and a crystal ball. Up to a week in advance, it can show us what the weather will do in Britain, down to a resolution of 1 square kilometre. And, looking decades into the future, it can give predictions for how our climate will behave across the globe.
When we think about what our models enable us to do, that we can actually simulate what we see going on outside, see our weather being simulated. To me, this is one of the great achievements of modern science. It's probably one of the unsung great achievements of modern science. Just because it's a computer code and therefore not visible doesn't mean that it isn't something that's a huge success. I compare it a bit with the human genome, mapping the human genome. It's a similar achievement. This is a remarkable coming together of science and encapsulating all our understanding of that science in these codes and producing something, a simulation, that looks so remarkably like reality. It's an extraordinary achievement.
This giant machine encapsulates everything meteorologists have learnt throughout the history of their science. Hard-earned insights gleaned from tragedies and triumphs alike. The early pioneers wanted to see what the weather had in store for us just over the horizon. And now, thanks to their legacy, we have the tools to see our whole planet at a glance and look hundreds of years into the